So today we're going to talk about conjugated systems, and we're going to talk about the stability of those conjugated systems. And I asked you last time to go ahead and review resonance structures again on your own. And so today we're going to jump in and actually work some resonance problems in class, and before we get into the stability of conjugated systems. So in each of these we can either draw a resonance structure or not. And if we can, we need to draw all the possible resonance structures. So looking at 10, first of all, can we draw a resonance structure for that molecule? Yes. We can. And how will we do that? From where to where?
The double bond to the positive charge.
Okay, so we're going to go from the positive, or from the double bond to the positive charge, right? So we've got C, CH, CH, CH3, two methyl groups there, positive charge. And so we're going to push the electrons from there to here to form a new pi bond, right? Let's see, so that's that carbon. And we end up with that cation. Which one of those is the major contributor? The top or the bottom? And why? We have a more stable carbocation. Both carbocations are what? They're not both tertiary, obviously, but they're both what kind of carbocations? What carbon are they on? We have a carbon-carbon double bond, and the carbon directly attached to it is called what? It's an allylic, right? So this is an allylic carbocation. So we can actually draw resonance structures between those and end up with two. However, the bottom one is the major contributor, right? How about problem number 11? Can we draw a resonance structure for that molecule? Yes? You feel like we can. Your gut's telling you right, but why is it telling you that? What can we do? Okay, so I can move this pi bond, or this pair of electrons in the pi bond, onto oxygen, giving it another lone pair, resulting in a carbocation on this carbon. Which one of those structures would be the major contributor? The one that's drawn, or the one that I just described? Why would you think the one I described would be the major carbocation? Okay, that's true. Oxygen doesn't like to have a positive charge. But what does this structure have that the resulting structure doesn't have for every atom? An octet. So what do we know about the octet rule? It kind of trumps everything, right? So this molecule, or this resonance structure for this molecule, I should say, every atom has an octet. So even though oxygen bears the formal positive charge, it's still more stable than the resulting carbocation because the carbocation will not have an octet of electrons. Okay? How about problem number 12? Can I draw a resonance structure for that? How would I move the double bond? So how would I move the double bond to interact with that cation? I could move that double bond right there, but in doing so, what do I have to do? I have to move atoms for that to happen, because I'll form a smaller ring, right? That's actually a reaction. And it might happen, but it's not a resonance structure. I cannot draw a reasonable resonance structure for this molecule, right? If we notice this is an allylic, right? So we have a pi bond, sigma bond kind of arrangement. This is a pi bond, sigma bond, sigma bond. There's really no way for us to adequately draw a resonance structure. However, chemistry will occur, but that's not resonance, right? So something will happen. That's not going to be a stable molecule. If we draw it, let's see what we got. We got here, we got there, and they drew in a couple of hydrogens. What's most likely to happen with that? To where? Not tertiary, right? But we can get a hydride shift. Yeah, what is the point in that? You tell me. There is a point to it. Now I've got resonance structures. Now I go from a non-resonant stabilized carbocation to a resonant stable to allylic carbocation. And I can draw resonance structures for this. But this we can't draw any resonance structures for, but chemistry can occur. Okay, so we could end up with something like a hydride shift. So don't confuse chemistry, actual reactions, with resonance structures. How about question 13? Can I draw a resonance structure for that? I can, and how would I do that? All right, so I'll take one of these lone pairs, doesn't matter which one, I'll make a pi bond between the oxygen and the carbon, and that will put what on the oxygen? A positive charge, and the carbon will be neutral. And which one of those will be the major contributor, the one that's drawn on the board or the one that we just described? The one we described, because? The octet rule, right? Very good. How about question 14? Can I draw a resonance structure for that? I can't. Chemistry might occur. The lone pair on oxygen might attack the carbocation. I would form an epoxide, kind of an odd epoxide, right? But that's not resonant, so I can't draw a resonance structure there. How about 15? And how? Again, moving the lone pair to form a double bond between the carbon and the oxygen. How about 16? How? Form a triple bond between the carbon and the oxygen. Move that lone pair. Make a new pi bond. That would give me a positive charge on the oxygen. How about 17? 17 is exactly the reverse of what we just did, right? I can move one of these pi bonds onto oxygen, giving it another lone pair. All of those things are valid resonance structures. You need to be able to know how to recognize valid resonance structures, and you need to be able to know which one's the major and minor contributors. Okay? Can I draw a resonance structure for number 22? And how would I do that? So, okay. So if I do that, what do we got here? We've got C double bond O, O minus, and then we got CH2, CH3. So you're suggesting that I do what? I move this pi bond to there? Well, let's just see. Doesn't make sense. It's a lot of charges, right? But you weren't far from off, because all I really have to do is also move this pair of electrons there, right? That's what you meant? Ah, okay. All right. Fair enough. Which one of those is the major? Which one of those is the minor? They're equal. They're equivalent. Those are equivalent resonance structures. And we know that equivalent resonance structures contribute an awful lot to the overall resonance hybrid, right? We would expect each one of these carbon-oxygen bonds actually to be the same length. And in any one that I look at, I would predict, if I just looked at this as drawn, I would predict that this is a shorter bond than this one. But when we look at it by X-ray analysis, we would actually find that both carbon-oxygen bonds are equal distance with an experimental error, and that both of them bear some negative charge, right? Because they are equivalent resonance structures. How about 23? Can I draw resonance structures for that? How would I do that?
Put the atomic make a double bond between the carbon and then break the double bond with the oxygen.
Yep. Which one of those is the major contributor? The first one? The second one? First one? Second one? You say second? Why do you say second? That's right. Right. In both cases, we've got a charge, so it's going to be the same. Here we've got a charge on an electronegative atom, a negative charge on an electronegative atom. I should be more specific. Here, that negative charge is on a carbon, right? Does that mean I could ignore this resonance structure? No. And in fact, in a future chapter, we're going to talk about these so-called enolates. Don't need to worry about that yet, but these are called enolates. And they do a lot of chemistry, and they act as good nucleophiles. And you might predict that the oxygen behaves as the nucleophile, but in fact, it's the carbon. Even though it's the minor contributor to the overall resonance hybrid, it's the carbon that is the nucleophilic atom in most cases. And we'll learn why that is. Okay, so resonance structures are very important in this chapter. How about 25? Did I hear a no? Nope, can't draw a resonance structure. How about 26? I can't really easily do, I mean, technically I could move the pi bond to one of the carbons and have a cation and an anion, but that would be kind of silly, right? But I really can't move that O minus anywhere without breaking some rules. So now we're going to say we can't draw any resonance structures for 26. Okay? So, given what we've been talking about, which carbocation in the list here is the most stable? It is B. Why is it B? It's tertiary and allylic. We have resonance, exactly right. A is tertiary, which would definitely be more stable than a secondary carbocation or a primary carbocation, but there's no resonance possibilities there. C also is allylic, but it's less stable than B because each resonance structure would be a secondary allylic carbocation, whereas for B, you can have a tertiary. And then D, that one's really unstable because it's a carbocation that's on a carbon bearing a double bond. And the geometry just doesn't work out, right? A carbocation wants to be sp2 hybridized and planar, right? Can't be planar in that with those bonds. And so that's really, those are called vinyl cations, and they are not stable at all. You can generate them, but they are extremely unstable. Okay? So the rules that you should have reviewed before coming to class, right, that we needed to think about for our problems that we just worked on. So rule 1, resonance structures with more bonds and fewer charges are more stable. We talked about that last semester. We talked about the fact that resonance structures in which every atom has an octet is more stable. So even though oxygen, in this example that you see here, has a positive charge on the right, it's the most stable resonance structure. It's the major contributor because every atom has an octet. Okay, so all second row elements, we want them to have an octet if possible, right? Rule 3, resonance structures that place a negative charge on the more electronegative atom are more stable. And we talked about that just a second ago in our enolate example. So here's another enolate, right? Carbon with the negative charge, oxygen with the negative charge. This is going to be the more stable resonance structure, okay? Now, what about charge separation? I didn't put that rule up, right? What do we try to do with charge separation? Do we try to maximize it or do we try to minimize it? We try to minimize it if the charges are opposite, right? So if we have a positive charge and a negative charge and there's no way to get rid of them, we want to draw the resonance structure that brings that negative and positive charge as close to each other as they possibly can be, because we know that opposites attract. If they are like charges, then we want them to be as far apart as possible, right? But when we're typically when we're talking about charge separation, we're talking about opposite charges. So let's look at another problem from the ACS study guide. Which of the four resonance structures contributes the most to the overall picture of the molecule shown in the box? D, A, B. Is there anything we can eliminate? Is there anything that violates any rules? C kind of looks weird. That's a gut feeling, right? That's how you take your test? Looks a little weird. Which one would you eliminate right off the bat? Okay, you could eliminate C. Does everything have an octet in C? Yeah, so it may not be the first one that I would eliminate. Which one doesn't have an octet for everything? D. That'd be the first one I'd eliminate, right? What else doesn't have an octet? B, right? The carbon on B also doesn't have an octet. I'd eliminate B and D right off the bat. And so I would go from 1 in 4 odds to 50-50. Why is it A and not C?
There's something weird going on with that line under the carbon.
I don't know. What is that? Is that a charge? Negative charge.
It's a negative charge.
That is a negative charge?
I think so.
I didn't even notice it.
If we think about this, this would have the negative charge on this carbon. This one has the negative charge on oxygen, right? All right. So we've already talked a little bit about the types of conjugated systems that we can have. We can have something like 1,3-butadiene. That's a conjugated system because you have a pi bond, single bond, pi bond, that kind of arrangement. We also see that here, pi bond, sigma bond, pi bond. We also see that in this octatriene, pi, sigma, pi. So all of these systems are actually, that you see that are labeled as conjugated, are truly conjugated because of that motif. The others are not conjugated. Why would the 1,2-propadiene not be a conjugated system? That's true. And what makes that not allow it to have resonance? Technically, you're right. I would have to move an atom when I change its hybridization. An atom would move. But what? If I move it, it's basically the same thing. I don't know that I would agree with that. Ah, right on it, right? So what are the two terminal carbons? What's their hybridizations? sp2, and what's the middle? sp. And how many pi bonds does an sp carbon have? It's got 2 pi's, but 3 bonds. Or in this case, 4 bonds. But if you think about it, carbons 1 and 2 have a pi bond, and let's say it's in this plane. Okay, so this is carbon 1, this is carbon 2, and the pi bond's in this plane. Where would the pi bonds be between carbons 2 and 3? Which plane? What angle to that? Perpendicular, 90 degrees. And so these pi electrons, p orbitals, and these p orbitals can't interact at all. They don't even see each other for all practical purposes. Because this pi bond is rotated into the plane of the node of the other pi bond. There's no way for me to push these electrons to the other system because they're 90 degrees to one another. We say they're orthogonal, right? Why is 1 pentene for yne not conjugated? Yeah, we've got 2 sigma bonds in between the pi's, right? There's no way to draw. The same thing for 1,4-cyclohexadiene. We got pi, sigma, sigma, pi, right? And so no way to conjugate those systems. So we would expect these unconjugated systems to behave like isolated pi bonds. We would expect the conjugated systems to actually have different chemistry because they're more stable. Okay, and we're gonna talk about that a little bit today. So if you look at something like 1,5-hexadiene, we really just have 2 pi bonds. We can do chemistry to pi bonds. We can add halogen across it. It just happens that it would happen twice, but nothing special would happen. We would just add, let's say we're adding bromine, we'd add bromine across this pi bond, and we'd add bromine across that pi bond, and we'd just have a tetrabromide. Nothing special. 1,3-butadiene, however, if we tried to add halogen across the carbon-carbon double bond, we would have some special things that we'd have to take into consideration because of its stability. And then in these so-called cumulines, where we have a pi-pi kind of interaction, right, or bonding, so it's pi, atom, pi, if you will. You can see clearly from this drawing a little better than using my hands. You've got 1 pi system in the plane of the board, which are these blue p orbitals, and you've got the other pi bond in the that is perpendicular or orthogonal to that pi bond that's in the plane of the board. So it's coming out and going back. And so these are interesting molecules. They do a lot of cool things, but they're not conjugated. Okay, so in a way, they are like 2 separate pi bonds that just happen to share a single carbon. Okay? Now, if we think about a conjugated system like 1,3-butadiene, we can have an S-trans conformation, and we can have S-cis. What does S mean? Why would we call this S-cis and S-trans? What does cis mean? On the same side. What does trans mean? So why do I need S? No, we're not talking about R and S. No, we're not talking about that. When you learned cis and trans before, what were we looking at? We were looking how things were in 3 dimensions about a double bond, right? Ah, that's right. S stands for sigma. So in the past, if we had that, we would say that that is a cis alkene, right? It is S trans because it's trans about a sigma bond. It is cis, S-cis, because it is cis about a sigma bond. Here we were talking about cis and trans around a pi bond, right? So it's a little different. And these 2 forms can actually interchange fairly quickly. Which one is the major contributor at equilibrium, the S-trans or the S-cis? The S-trans. If I gave you 1,3-butadiene, put it in an NMR tube, and told you to go get an NMR of it, you would actually be able to distinguish these 2 protons. They would be shifted slightly differently from the S-cis. And you would have trouble finding this because the S-trans is so much more stable. Why is that? Yeah, you got the big groups as far apart as we can get them, right? It's just a conformation. We're looking down the conformation about that bond. And if we have that, we would see that the 2 groups are what with respect to one another? Anti. And in the S-cis, they would be? Yeah, okay. Eclipsed. Yeah, they're totally eclipsed, right? And we know that that's not very good. So this is going to be the most that you'll have in this solution. This would be the least amount. And in fact, this is like 99.9999 something %. You have very little S-cis, although it can happen. It can rotate, and we can rotate because this is a sigma bond, right? We can rotate around sigma bonds, okay? Now, if we look at these conjugated dienes, what we'll notice is that the carbon-carbon double bond is around 1.34 angstroms on both ends, and the sigma bond between carbons 2 and 3 is about 1.47 angstroms. What's interesting about that? If I look in the data in the box over to the side for comparison, what stands out about that? The sigma bond is a little shorter than you might expect, right? And why would we expect the sigma bond to be a little shorter? Why would we expect that sigma bond to be a little shorter than a typical sigma bond in an alkane? There's actually two reasons. One of them has to do with the pi bonds, and why does that matter? I'll buy that, but why? What can I draw for this? I can draw a resonance structure, right? I can push my electrons, and I can draw a resonance structure. Remember that structure from the first day? And I told you that this was the major or minor contributor. It's minor, but even though it's minor, it tells me that this bond has some double bond character to it. And what do I know about double bonds compared to single bonds? They're a little shorter, right? And so resonance is telling me that this bond should be a little shorter, right? Resonance tells me that. That's answer number one. There's another plausible answer. What might it be? What's the difference between this sigma bond and a sigma bond that's in an alkane? Hybridization. The orbitals that are overlapping are different. In ethane, the orbitals are all what? What kind of hybridization? They're all sp3. And so I have an sp3 orbital and an sp3 orbital overlapping. In this molecule, what do I have? What are the hybridization of the orbitals? They're sp2s, and so I've got an sp2 and an sp2 orbital overlapping, right? And if we look at that, what we recognize is that an sp2 orbital is actually a little smaller than an sp3 hybridized orbital. Why is that? Why is an sp2 hybridized orbital smaller than an sp3 hybridized orbital? Less p character, right? This starts to look more like a p orbital, right? And p's are kind of big. This looks less like a p orbital, but it looks a heck of a lot more like a p orbital than an sp. sp looks like more like an s orbital, right? And so if I take two short things and I try to overlap them, am I going to get something that's longer? Not at all. It's like me giving you two pieces of string that are a certain length and asking you to make it longer than that. You can't do it, right? You can't line them up like that. So there's two reasons why this bond is shorter than you might predict. One has to do with the resonance contribution, and the other has to do with the orbitals that are involved, okay? Now, all this conjugation results in increased stability. And we talked about last semester a lot when we were talking about resonance structures, that the more resonance structures you can draw, the more stable it was. And I told you that we can measure that stability. And one way in which we can measure that stability is to actually do chemistry. So if I take this isolated 1,4-pentadiene and I hydrogenate it, I add hydrogen across the carbon-carbon double bonds. Notice we're using a catalyst, right? I get pentane. If I take this conjugated diene, 1,3-pentadiene, and I hydrogenate it, I get pentane. So what are these with respect to one another? Well, one has resonance, one doesn't, but what are they with respect to one another? They have the same molecular formula, do they not? But so what are they? They are not resonance structures, but they are isomers. These two things are isomers. And so when we hydrogenate these, we get the same product. Okay? But do we get the same amount of energy out when we hydrogenate them? And why is that? That's right. So if this is pentane on the energy diagram, this table, where would we put the 1,4-pentadiene and where would we put the 1,3-pentadiene in terms of an energy diagram? If this is the energy axis and this is pentane, where would I put the conjugated one? Okay, maybe here. And where would I put the non-conjugated one? All right, maybe a little higher, right? So when I hydrogenate this one and it goes to the product, it has farther to fall, right? That's more energy, right? Throw a brick out of a 10-story building versus throwing a brick out of a 5-story building, more energy, right? Okay. So this one has less distance to fall. And so what's this difference between the two? It kind of is a delta H in a way, but that's not what I'm after. It's the resonance stabilization energy, right? Because they're isomers of one another. The only difference between them is one's conjugated and the other isn't. And the difference between this one and this one is the amount of stabilization energy you get by simply having those pi bonds in resonance with one another. So if we look at the math here, right, we're looking at about 7 kilocalories per mole difference. That's a lot of energy, okay? This one's stable, more stable by about 7 kilocalories per mole of energy, okay? So we've just talked about that an awful lot, so let's skip that. And let's actually do some other things in about the 15 minutes that we have left in class. So, I think everybody will agree that this is a conjugated system, right? 1,3-butadiene. And what can we do to carbon-carbon double bonds? We can break them. We can add things across them, right? We can do chemistry with them. Now let's suppose that Holly comes into my lab and she has 1,3-butadiene, 1 mole of it in some vessel, some kind of magical vessel. And in another vessel, she has exactly 1 mole of HBr. And only 1 mole of HBr. And she mixes the two together. What's going to happen? Okay, we're going to add HBr across the across a carbon-carbon double bond, right? Which carbon-carbon double bond? Does it matter or does it not? Okay, let's think about that. You're making the mistake I want you to make. Is that a single system or is it 2 carbon-carbon double bonds? It's a single system because it's in resonance, right? It's in resonance. It is 1 pi system, right? It is a single pi system. So, what can happen? There are actually 2 possibilities. I've added HBr in a Markovnikov fashion across the carbon-carbon double bond. Nothing new. Or I can add HBr across the pi system. Okay. That's the next step, isn't it? Now we got to figure that out. So, can we distinguish those 2 products by any technique that we know of? How could we do that? What experimental technique might we use to determine whether we had the top product or the bottom product? You think you could tell by IR? Probably not. Could you tell by NMR? Absolutely, you could tell by NMR. You could distinguish the two. So, Holly has come into my lab. She's got her magical vessel of the alkene, or the butadiene. She's got her magical vessel that has exactly the same amount of HBr. She's mixed them together. What are the conditions? What's the temperature? What's around? She just walks in. She's doing this at room temperature, right? So she does this first at room temperature. She takes a sample. She goes and runs it by NMR. She comes back and she says, at room temperature, I got this product. Being the smart person that she is, she says, I wonder what happens if you run this at really low temperature. And so she sets up a dry ice bath. It's minus 78 degrees. She puts her magical vessel in there so that all the reagents are at minus 78 degrees. She mixes them together, lets the reaction occur. She goes and runs an NMR, and she finds out, lo and behold, at minus 78 degrees, she gets that product as the majority product, okay? And it turns out that it's about, at this temperature, you get about 80% of this and about 20% of this. And at room temperature, you get about 80% of this and about 20% of that. Temperature matters here. Now, I'm going to challenge you right now. Why does temperature matter? How am I going to figure that out? We have an experimental observation. Holly now has to come up with a hypothesis. What kind of hypothesis can we form? Close. It does.
Would we first have to decide which one had like a higher energy and increased there?
A higher what?
Higher or lower energy?
What energy are we talking about?
Just stabilization, I guess.
Okay. Don't think that gets us where we need to be.
Resonance happens faster in room temperature?
Nope.
Okay.
Resonant structures are more or less unaffected by temperature. But what do we know about things at low temperature? They move slowly, don't they? The solvent gets more thick, things move slower, right? So maybe it has something to do with how quick an atom can move. So let's think about the mechanism. And let's not worry about temperature yet. We'll get back to that. What would be the first step in this mechanism? The bond picks up a hydrogen. What bond? A double bond picks up a hydrogen. It doesn't matter which one right now, because they're equivalent, right? But is it going to go to the most substituted or the least substituted carbon? Whose rule are we going to play with here? Markovnikov's rule. And he tells us that the hydrogen goes to the least substituted carbon, or the carbon with the most hydrogens, right? Which would be, I'm just going to use carbon number 1. So the first step of the mechanism is going to be this. Protonation of the alkene. We end up with, let me just draw the bromide down here, with that intermediate carbocation. Is that a stable carbocation? More stable than a primary. It's secondary, and it's allylic, right? So what do I know about this allylic carbocation? I know I could draw a resonance structure for it, right? So I could draw the resonance structure for this. And I'm not moving any atoms. The bromine's exactly where it was before, even though my drawing may have not dictated that. Right? What does this tell me? What do these resonance structures tell me?
Something about the temperature,
Okay. What else? Where can my bromide attack? It could attack technically at either place, right? I could attack the secondary carbon because it's got positive charge there, or I can attack the terminal carbon, right? All right, so we can attack either carbon. We all agree with that. At low temperature, it must be doing what? Well, they're both allylic. Which allylic carbon, top or bottom? The top one, right? So we end up with that product that we have there at the top. Why would that happen at low temperature? If we think about it, this hydrogen and this bromine were really close to one another when it protonated the double bond, right? They were attached. So is this bromide closer to this carbon or this carbon? Closer to this one. And at low temperature, is it going to have, it's not going to move as readily, right? So this happens quite quickly, and you end up with that product, right? Would we call this the kinetic product or the thermodynamic product? Why would we call it the thermodynamic product? Okay, that's true, but for the wrong reason. It's actually the kinetic product because it's closer and that reaction can happen faster, right? It's about how fast the reaction occurs, right? So this, at low temperature, this is called the kinetic product. At high temperature, we get this product. This is the thermodynamic product. Okay? Now, thermodynamic means the most stable product. That product there at the bottom is more stable than the product at the top. Why is that? You tell me, why? Which one's a terminal alkene? The top one. Are terminal alkenes more stable or less stable? Less stable. The bottom one, the alkene, is a disubstituted alkene, which is more stable than a terminal alkene, right? See how things are starting to come back from 255 and getting integrated in all this chemistry that we're doing, right? So the thermodynamic product is the most stable product. The kinetic product is usually the least stable. However, it is possible to have a product that is both kinetic and thermodynamic. There are examples of that, but we're not going to get into that today. I just want you to be aware of it, okay? Now, the interesting thing for this, let's say Kara comes into the lab and does the exact same experiment at low temperature. And she isolates the kinetic product, 80% at low temperature. She puts this in an NMR tube at room temperature, and she watches the NMR. She takes an NMR at, say, 10 minutes after the reaction, then 20 minutes after the reaction, then 30 minutes after the reaction. What is she going to start to see? She will see it rearrange and form the thermodynamic product. These are actually, you can equilibrate from the kinetic product to the thermodynamic product. Now, it may take years for that to reach equilibrium. It depends on how high the energy barrier is. But it's very important for you all to know the kinetic product always forms first, even at high temperature. And that makes sense because the bromine's right there next to that carbon, isn't it? It will form first. But at high temperature, it can equilibrate to the more stable thermodynamic product. It just so happens in this reaction that equilibration is very quick. But the kinetic product always forms first. If you think about an energy diagram, that's the shortest mountain to climb. It's got to go over that and form that product. Okay? Thermodynamics indicates that. So we're going to form the kinetic product first, and then it equilibrates to the thermodynamic product. So we can add things across carbon-carbon double bonds like we normally think of it, or we can add things across a pi system. And everything that we've added across a double bond before, we can add across a carbon-carbon pi system that's part of a conjugated system. And I'm only dealing with two carbon-carbon bonds here just to keep it simple for us. But we could also add bromine across the carbon-carbon pi system, and what two possible products could we get here? Show me where to draw the bromines. Okay, I could add bromine here, right? Or I could add bromine like that, right? And I'm drawing sloppy, I apologize. But we can add things across these pi systems if we're very careful with how much reagent we add, right? Again, we have to be careful to have only 1 mole of this and 1 mole of that. Because if I have an excess of this, it will simply start to add to the other pi bond, right? So we have to be careful. But these conjugated systems behave as a single system, and they can have some unique chemistry. And it's because of resonance, okay? So with that, I'm going to call it quits for today. We will have, when we get back, so we don't have class Monday, right? When we get back on Wednesday, we will have an inverted lecture. We will be going over the Diels-Alder reaction. I will post that to YouTube. I'm going to give a lecture on the Diels-Alder reaction. But you all need to read that and watch that video before you come to class on Wednesday, okay? All right. Happy Mardi Gras.